Kasper, floor is yours.
Thank you, Manus. 6 or 7 years ago, I started swimming. I went to the swimming pool almost every day. I tried to learn the front crawl, and that's when I discovered that swimming is pretty hard. At some point, I asked someone who was clearly a better swimmer than me to help me a little bit with my technique. So he agreed, and I swim a lane, and he gave me some feedback on that, and I got a little bit better. But the problem with this approach is that he could only give me feedback once I finished the lane. So everything I do in between, I just have to trust myself of doing right. Wouldn't be nice if it was possible to actually feel when you're doing something wrong, get a vibration or something like that. At the moment that you're doing the fault, of course. So that's where my thesis topic comes in. Swimming with concurrent haptic feedback. Concurrent meaning as the action is happening, and haptic feedback referring to vibrations given by an electronic device. So, I'm first going to tell you a little bit about the background, then about what I have developed here, then a little bit about the evaluation of the wearable, and in the end, some conclusions. Well, we start with the background, and then we are going to look at what is already out there in a sense of concurrent feedback for swimming. I found 5 different systems. The top 3, as you can see here, they make use of auditory feedback. For instance, the informative pedals, they measure the pressure you exert with your hands on the water and give feedback if the pressure is high enough. The bottom 2, they make use of visual feedback. The visualizing in goggles has an RGB LED in the goggle, so it can tell you whether your stroke rate is too slow or too quick. But none of them are haptic feedback. So this is something novel, something that hasn't been tried before, or at least hasn't been published. And I think it can really add something, certainly for more design capabilities. Because when you're using haptic feedback, you don't need to have any electronics near the face or around the head. So let's start a little bit, let's talk a little bit about swimming. I'm going to focus on the front crawl and the backstroke. The front crawl, because that is the most common and swim stroke in swimming, because it's the quickest, and the backstroke because, well, it's pretty similar. So we can use the same concept. So the idea of improving swim technique is pretty simple. For the same amount of energy you spend, you want to either increase your propulsion or decrease your drag. So to find something to give feedback on, we need to find something that improves one of these aspects. Luckily, someone else, Mr. Bachlin, has already asked a couple of swim coaches about this. So he asked them to rate a list of faults from most detrimental for the front crawl to least detrimental for the front crawl. And as you can see, bad body balance was at the top of that list. He also asked for which they would like to have technological help. And there, bad body balance was also quite high. So eventually, I chose this thing to give feedback on. What is bad body balance? Well, here you can see an example. The bottom swimmer lays a lot flatter and higher in the water. That means that there is a lot less water hitting him while he's swimming. And in that way, you have a lot less drag. You need to move a lot less water out of the way. So, now the research question becomes, how can a wearable device be designed to improve body balance in swimming with the use of haptic feedback. For that, I also came up with a couple of sub-questions. So, the first one is, how can a wearable be made water-resistant and provide haptic feedback? Then we have, how can a wearable be designed for multiple body types and as a platform to explore haptic implementations? We have, how can haptic feedback be made more perceivable in an aquatic swimming environment? How can haptic feedback be implemented for providing feedback on body balance? And finally, how can the system be evaluated? Now we need something, well, we need to make something to actually give the haptic feedback, of course. So we start with the electronics. For that we need a brain, which needs to be powered by a battery. And we have a sensor, an IMU sensor in this case. This is an inertial measurement unit that makes use of angular velocity and linear acceleration, and with some trickery, some mathematics, you can figure out the angle with regards to gravity, and thus also the body balance. Of course, we need haptic motors, so we can give the feedback. We need some storage, and we also need an interface. In this case, that's an LED to give the status. So if this now in idle mode, for instance, and a button, so we can actually change the status. It needs to all be protected against the elements. It's a pretty harsh environment in the swimming pool, so we need to waterproof it. What I found was that using a silicone lining in a 3D printed case and then bolt it down seems to work quite well. So that's what I did. So for that, I made a custom mold for making a silicone sleeve, in which we put the electronics and the housing around it. This then gets bolted onto a plate, as you can see here, with another silicone pad in between, so it's really watertight. And then we have the battery pack connected with some wires to the haptic motors as well. All right, then we come to the harness. I started out using a waistband like this. The problem was that this would shift around during swimming. So eventually I ended up using a harness like you see here. And this seems to work great and doesn't move around as much. Then we also need to make sure that you are actually able to feel the vibrations. For that, I did a perception test. So I went into the water, I put the vibration motors at different points on my body and actually tried to feel where you could feel the vibrations. What I noticed that you might want to avoid the water noise. By that I mean that, well, during swimming there's a lot of water rushing down your body, which all interfere with your skin and makes it more difficult to actually feel the vibrations. I also noticed that pressure helped, so putting it underneath the bands of the wearable made sure that, gave a little bit more pressure, which made it easier to feel the vibrations. And in the end, I came up with 3 candidates for further testing. We also need a haptic pattern. So you need to know when your body balance is not good enough. So the easiest way to do this is just choose a threshold and turn on the vibration motor. What you can also do is make it a sloped variable. So as soon as you make a little mistake, you get a little bit of vibrations. The problem with this is that it was already pretty difficult to feel all the smaller vibrations. So to counter this, I also thought of a third way, and that was a modulated pattern, in which the on time and the frequency would increase if your body angle would be larger. So we got the haptic patterns and the locations. So I got 3 people together to actually help me evaluate the wearable. They tried 3 to 4 different locations on the body, depending on what they wanted, and also the 3 different patterns that I designed. I asked them about the perceivability, about their preference, and if the feedback was clear. From that, I found that the swimmers were able to feel and change the feedback based on their body balance. I also noticed that both binary and sloped were perceived as binary feedback. So they didn't really feel the difference between a soft vibration and an intense vibration. But the difference was that the sloped pattern was perceived as more graceful or less annoying. The modulation pattern was unclear. For the placements, they had a preference for places where they could feel the vibrations the best. It didn't really matter for their intuition which place was the best. So, the final prototype consists of this harness with the wearable in the back, the 2 haptic motors in the front on the ribs, and I used the slope pattern. So, this is what we are going to try and evaluate. For the evaluation, we want to test the difference between haptic feedback and no haptic feedback, to make sure that we don't have to have too many participants. I'm going to do within participant testing, meaning that every participant would do a control and a test condition. For the acquisition strategy, so recruiting the participants, I used a convenience sample, mostly people here from the UT, and I focused on people who were able to swim but still needed to improve their technique. And eventually I found 18 participants to help me. The problem with just taking the raw measurement data is that everyone's physiology is different. So you can imagine that some people have a more straight back and other people have a more hollow back. And that makes that it's difficult to compare between people. To mitigate this, I'm going to compare the amount of difference between the different test conditions. For an example, this is test data that I recorded of someone doing 6 lanes of backstroke without any feedback, and then 6 lanes of backstroke with feedback. We'll take out everything that doesn't have anything to do with the free swimming phase, or the phase where you're just swimming front crawl, backstroke in this case. So all the turns and all the passes in between. We can then take an average of all of these points and also take an average of the points within a certain condition. If you then take the difference between the overall average and the average between the test conditions, then we get what I call the RABA, or the relative average body angle. So I first did a baseline where they had to swim 6 lanes of front crawl and 6 lanes of backstroke. Then they got feedback, so in the baseline they didn't get any feedback. And then they did a retention session to see whether they would retain their newly acquired body balance. So these are the results. I got these results by doing let me check real quick, a repeated measures ANOVA with post-hoc pairwise t-test and a Bonferroni correction. Yes. Yes, and you can see here we have the brackets above the box plots. Those brackets indicate whether something is significant or not. So the difference between the baseline and the feedback for both the front crawl condition and the backstroke condition is here indicated as significant. That means that the participants were able to improve their body balance during the experiment. There's also a significant difference between the baseline and the retention during the front crawl, which might indicate that they were able to retain their body balance, at least to some extent. For the backstroke, it's not significant, so it's not clear. So a little bit of discussion about the evaluation. The participants also reported getting feedback from the body roll. That is the rotation in the polar or vertical axis, so to say. Yeah? Cool. So that has definitely influenced the way that they reacted to the feedback. There was also that we were able to show motor acquisition. But motor acquisition is something else than motor learning, which means that they actually acquired a new skill. So to really prove motor learning, you would need to do another experiment at a later date, a post-experiment. There's also that there's influence just from being tested. So if they start swimming and I ask them like, okay, now we have this feedback and it reacts to your body balance, they will automatically change their position, maybe despite of the feedback. So let's come to a couple of conclusions. I'm going to answer the sub-questions real quickly, and that's how I answer the main question. So I was able to make a water-resistant haptic, water-resistant wearable using a silicon lining. It was designed by multiple body types by using elastic straps that are adjustable, and I had the vibration motors on wires so I can test multiple locations. The feedback was made perceivable by using fairly large haptic motors, as well as the right location to give the feedback. The feedback was implemented using a sloped pattern on the front here on the ribs, and the system was evaluated in which we saw an increase in motor acquisition. So that is how we answer how a wearable can be designed to improve body balance in swimming with the use of haptic feedback. Now I want to tell a little bit about the positioning of this research within the concurrent feedback for swimming research. So haptics is a novel approach. And it has the possibility to alleviate some of the previous design constraints, like putting electronics near the head, which is very useful for swimming because there's already a lot going on, and stuff around your head, well, it gets annoying. There's also a lot of promise for future implementations because of this. You can put the sensors at different places, and it showed that there was a measurable difference. The people who also joined my study had a positive sentiment towards the use of such a device. So for future research, I would suggest doing more hardware iterations, maybe start with actually making it user-friendly, because right now I am the only one who is able to change the settings on this thing. And it also doesn't recognize when it should give feedback, only if you are already doing that activity. And have fixed wiring so it doesn't get tangled up and it's easy to put on and take off. I don't know what this is. Oops. Thank you. That happens. I would also suggest to do an extended experiment to show motor learning to take this to the next level, using a proper pre- and post-testing with a controlled test and placebo group with expert swim evaluation. Make sure that we can actually prove that this is viable and that and we can maybe commercialize it so that more people can make use and be more autonomous and less reliant on coaches. So, haptic feedback during swimming is a novel concept that shows promise in helping swimmers improve their technique. Thank you.